All right, section 1.3, we're going to look at our third way of evaluating limits. So in section 1.2, we looked at graphical and numerical, right? So they're graphs and tables. And today we're going to look at algebraically, or it's also called analytically. So those two words, you'll hear me use them interchangeably because they're used interchangeably throughout calculus, okay? So jot that down. When I say algebraically or I say analytically, it means the same thing, right? So the first thing that we're going to look at is some basic limit properties. And we can kind of justify these from what we've already learned in section 1.2 about graphs and about numerical tables, right? So if you have the limit as x approaches c of a constant, if you think about what the graph of like y equals, and we'll make up a number 5, looks like, it looks like a horizontal line, right? And remember, any point on the horizontal line, it doesn't matter where it is, the y value is the same thing. So if I'm looking at this particular point, we'll call it C. No matter what C value I pick, y is still 5, right? It doesn't depend on what that is. So you see that the limit itself, as x approaches C of the value b, is simply b, okay? The constant graph, it doesn't change. So the graph is always the same y value. The next one is much like the graph of y equals x that it's describing. So if you have the graph of y equal x, it looks like this. And along every point of that line, whatever the x value is, the y value is. And that's what the equation means. So thinking about the graph or thinking about the equation itself, what this is saying is that the limit as x approaches c of x is simply c. Whatever the x value is, the y value is. So this one's saying that x value is c, so we end up getting an output value or a y value of c. Remember, limits are y values or output values. The next one requires a bit more, and we'll talk more about it later, but suffices to say for the moment that the limit as x approaches c of x to the n is c to the n. And you might get the feeling of, are we just replacing x with c? And in very many ways of what we're going to be encountering, it feels like that's what's happening, right? The x value gets replaced by c, so x to the n becomes c to the n. So these are our three sort of basic limit properties. Everything else we're going to do builds off of this, and they build off of this in the way that seems reasonable. You should look at this and go, that sort of makes sense. I can see what's happening here. We're going to encounter some other properties as we go through the semester where it doesn't feel quite so straightforward. But these should feel very straightforward. So if they're not feeling like they make sense, we should talk. And you should come see me so we can make sense of them. Because these should feel like, that makes sense. So there are 5 more, I think it is, properties we're going to take a look at. Some conditions that are written in just for us to be able to work through these at the top is b and c are real numbers, n is a positive integer, f and g are functions that have limits, so nothing that doesn't exist. And the limit as x approaches c of f of x is L, and then the limit as x approaches c of g of x is k. Okay, so we're looking at these k's and these l's. That's where all these letters are coming from. And what this is telling us is that everything we expect to happen should happen. So when I have a scalar multiple, right, like this b that's in front of f of x, I can pull the b to the beginning of the equation. So you can very much see like this piece is coming out here in front. And what I'm left with, this piece and this piece together, is exactly what's going on here. There's the L. So I end up with the b that I pulled to the front times L. And that should feel like, yeah, okay. The second one talks about what happens when we add and subtract functions. Well, we should kind of feel like, well, can't we just add and subtract their limits? And the answer is yes, we can. So when we have f of x and g of x either added or subtracted, and we take the limit, we can just find the limit of 1, like the limit of f of x, which is L on this one. And we can find the limit of g of x, which is k, and we can either add or subtract those two limits to get our final quantity as well. Again, what we expect to happen should happen. And then the next one on this screen, not the last one, but the last one on this screen, talks about the product. And again, can't I just do the product of the limits? And the answer is yes, it can. So I can take the limit of f of x that's L. And I can take the limit of g of x, that's k, and I can just multiply L and k together. What I expect to have happen is going to happen. There's two more. Does everybody have those three written down? Not quite? Okay, let me pause. So these three, and then in the next one, they compose the four basic operations. The first one is a scalar multiple. That's not exactly a basic operation, but we're going to see it come about many times. The second one has the addition and subtraction. The third one's multiplication. And the fourth one we're going to get here in just a minute is going to be division. Okay? So if you haven't been printing them out, I see a lot of printouts, but maybe not everybody has. Remember, these notes are online, and I would encourage you to print them out. So the fourth one is the quotient. All the stuff at the beginning is the same. So the quotient tells you, again, well, what happens if I have, division? Can I just divide the limits? And again, the answer is yes. And there is one caveat. What can a k not equal? 0. And that should make sense. Why can't k be 0? We can't divide by 0. Now, we are going to talk later about what happens when the limit of something that we're dividing by does approach 0, but that's not today, okay? So it's not that it can't happen, it's just that this rule wouldn't apply in that situation. All right, so as long as we don't have 0 in the denominator, we can simply divide the limits. And the last one's called the power rule, and it looks a lot like the rule number 3 that we saw on the last set. It says that if we have a function raised to a power, we can evaluate that function's limit, like find that function's limit, which was L, and we can raise that to the power. So very much like x to the c can be changed, x to the n can be made c to the n. This is f of x to the n can be made L to the n. It's just that it's more general, right? The function doesn't have to just be x. It can be anything, and we can do the same process. So our goal in this section, for the most part, is to use these properties. But the reality is that once we start using these properties, you're not going to feel like you're using the properties because they're so embedded in what you're expecting to have happen anyway. So the first one, maybe two, I'm going to sort of point out to you, hey, you're using this property. But then after that, I'm going to stop because you're just going to be doing it the way that you would expect to have done it had I never shown you any properties anyway. Okay? So the first one we're going to take a look at is the limit as x approaches 1 of negative x squared plus 1. So the properties that are really in place here are addition. You see the addition, right? You see x to the power of 2, right? There's a variable to the power 2. You see a constant property happening. So if we're going back through and looking at these properties, you could say that we're using number 1 because there's a constant. You could say that we're using number 3 because we have x to a power. And you could say that over here we're using the sum and difference, number 2. All those are in play. But what does it really look like when we do the problem? Well, it really looks like we just replace the x with the number 1. So what we actually really write down is negative 1 squared plus 1. So for the purposes of doing a quiz, which you'll have to do next week for me, I think it's on Friday, or the purposes of doing a test, you're going to write this one step and then grab your calculator and you can evaluate it. That's fine. But I want to see that you understand that the replacement is what's happening here. Do be a little bit careful if you're thinking through this on your own. We want to make sure that the 1 is being squared, not the negative 1, right? And if we've been given a negative 1, that we make sure we actually square the negative. So just be careful with your parentheses and your notation for that. So if I have this value, negative 1 squared plus 1, what does it give me?
0.
It's 0. Okay? So it's the behind-the-scenes properties that are happening, but the in front of what we're really doing is just evaluation when we can. So if you take a look at the next one, same thing. But we got more properties going on here, right? You see lots of properties here, in fact. We see some subtraction. We see some addition. We see division. We see constant multipliers, right? That 2 times the x is a constant multiplier. We also see addition is, no, I said the addition and subtraction. I think that's all of them. So we have addition, we have subtraction, we have the quotient, and we have the constant multiplier. Yeah, I think that's it. We have all four different properties on this one. But again, what it really looks like when we do it is replacing x with -3, right? So this is 2 times -3 minus 3. And then I have -3 plus 5. And if you do some simplification, you'll either get a fraction -9/2, or you can get the decimal -4.5, or you can even do a mixed number, that's fine. Basic rule of thumb is if you have a terminating decimal, like 4.5, that's fine. If this had said 4.3 repeating, we would not put a repeating bar. That's just not done in mathematics outside of like junior high and maybe a little bit of high school. So once you get to this point in mathematics, we're going to keep things precise and exact, which would mean keeping them in an improper fraction form. You could put it in a mixed number form. That wouldn't be altogether awful, but it's also not necessary. So -9/2 is perfectly reasonable. So either of these answers will work on this. Okay, so all of this works really fine, but what would happen if we had on this one x approaching -5? It wouldn't fit one of our properties, right? It wouldn't fit one of our properties. And so what we're going to encounter in a little bit more in this section is those properties. What happens when I do have that 0 showing up in the denominator? What are my options then? Before we get there, I want to point out 3 other properties that sort of come about from the basic properties that we did before. And again, they aren't something that you're going to be thinking about most of the time when you're using them. They're the behind the scenes like reality of what's happening and why you're able to do what you expect that you should be able to do. So there are 3 different, well, there's 4 actually, because 2 of them are merged together in this one, 2 of them are merged together. So there's 4 different properties that we want to pay attention to rather, for what happens with polynomial, rational, and then radical and composite functions. So this one merges, this theorem 1.3 merges together polynomial and rational functions. So polynomial functions, those are things like x cubed plus 7x plus 2, right? Lines are polynomials, 7x plus 2. We can do powers that are really big, like x to the 52 plus 7x plus 2. I don't know why I keep going 7x plus 2, but that's just my thing today, okay? So polynomials. Polynomials have the ability to always simply be evaluated in, always. So whatever the limit is x approaching, that x is approaching, we can plug it in. And we saw an example of a polynomial. Whoops, too many back. Number 1 here was a polynomial. It will never have any problems with denominators because it didn't have denominators. So you will always be able to simply evaluate a polynomial function when you're looking for its limit. Basically what it's saying is that its limit is exactly the same as its function value. Now that's not true for every function, but it's true for polynomials. Okay? And that comes about by all those properties that we discussed already. Second one, rational functions. You'll notice this rational functions one looks a lot like the quotient one we saw before. And it's saying much the same thing as the polynomial. I can simply evaluate. Just put the number in unless it makes the denominator 0. That's what I was alluding to over here on number 2. If I let x approach -5, we got to pause and say, well, wait, that's something else is going to happen because that denominator is 0. But as long as that doesn't happen, like number 2, we're simply evaluating. And again, why? Because of all those properties that we developed on the previous 3 slides. Okay? So we can do that for rational functions. So polynomials and rationals, we simply evaluate them. Not only that, but radicals have the same thing happening. So when I have a radical function, right, the nth root of x, it becomes the nth root of c. Now there's a little bit of like language after this that's sort of giving some condition statements. It says this is for all c, but then it says when n is odd, and then it says, and it's valid for c greater than 0 when n is even. So let me just tell you what that's saying. When n is odd, you have things like cube roots, and 5th roots, and 7th roots. And when you have those odd powered roots, you can have negatives underneath the radical, right? I can take the cube root of negative, do negative 27, make it easier. The cube root of negative 27, I can do that. It's negative 3. However, if I have an even root, like a square root, a fourth root, a sixth root, right, even powered roots, I can only have positive numbers underneath the radical. And it's probably a good point for me to point out that you're probably thinking, well, what about imaginary numbers? So calculus, at least the calculus that we're doing in this course, plus all the way up to Calc 4, is done on the real number system. So what do you do with imaginary numbers? You take another course, right? There's another course called complex numbers, and that's where those kinds of things show up. But that's not what we're working with traditional calculus. So we're using real numbers only, which means underneath the radicals that are even roots, we have to have a positive number, and that's what that second statement is saying, okay? So again, as long as it doesn't make what's underneath the radical negative, we're able to simply plug in x as c. And then the last one in this section talks about composite functions. And if you remember, composite functions are functions embedded inside of others. So let me just give you an example of a composite function. If I were to have, I'll just give the name h of x, and I had a square root, and inside of the square root there was like a 4x to the third plus 7x. So the function that's inside, I even put it in parentheses so you can see it, is embedded inside of another function property that's square roots. So you have two separate functions going on, one's inside of the other. That's a composite function. You encounter them in algebra, and you spend some time dealing with them there. But again, this is saying the same thing. Okay, fabulous, but that just means that I evaluate the x value in as c. As long as it meets the other conditions, doesn't make denominator 0, doesn't make negatives underneath radicals, right? All the conditions we had before, I still have the same ability to simply let x equal to c. And you might be asking yourself, well, isn't that all the functions there are? And very nearly, at least in terms of the ones we're going to be working with. It doesn't quite get us to trig. We'll talk more about trig later. If you haven't had trig recently, might be a good time to brush up on some of your trig stuff. But we'll get to the trig properties. I think it's later in this section. If not, it's the next one. All right, so all of these properties still lead us down the same path that say, just take the x out and put c in. Just take the x out and put c in. So we're going to take a look at doing that for some functions. Okay, so if I were to simply put in 3 for x now that we've learned that we certainly can, we're going to run into a problem on this one. What problem do we run into? Yeah, and I like the way that you just said that, Josh, because we end up with 0 on the bottom is important, but the fact that there's a 0 on the top tells us something more. So if you put in 3 for x in this problem, you do get 0 on top and 0 on bottom. Okay, if it was just a 0 on bottom, it would be a different situation. But when we have a 0 on top and a 0 on bottom, it tells us something. What it tells us is it tells us there is a way that we can eliminate the problem. And it involves factoring. So we go back to the original problem that we were given and we attempt to factor what's on top or on bottom or both, depending on where we're working, okay? So the numerator in this case doesn't really have a whole lot to be done with. It just is what it is. There's not any factoring that can be done, at least not when we look at it at the moment. We'll talk a little bit more about that in a minute. But we're going to attempt to factor the denominator. So the top is 3 minus x. How does the denominator factor? Remember?
Plus 3 times x minus 3.
Excellent. And again, if factoring is kind of a rusty spot for you, might be a good time to brush up on some of those skills. Success Center is a great place to do that. My office is a great place to do that. I can get you some practice on that if you need some. Let me come and let me help you. So that's a difference of squares. If you're looking at that and going, where did that come from? It's a difference of squares property. And if we look at the numerator versus the denominator, they don't have any perfectly identical pieces, but there's a piece that is close to what the numerator and the denominator are the same. So which piece in the numerator and the denominator is almost the same? Yeah, the x minus 3 on bottom and the 3 minus x on top. The only thing different is the sign's in the wrong place, right? So what does that mean? Well, it means that if I would have taken the numerator instead of writing it this way, and I would have taken a negative out of it, it would have been x minus 3 as well. So if I pull a negative out of the numerator, I get that x minus 3 and the x minus 3's match. It's not the only way to think about it, but it's a pretty decent way to think about it. You can cancel the x minus 3's and you get a negative 1. The other way that you can think about it as a pretty reasonable way to think about it is that when they do match perfectly, except the signs are different, you can just realize that they're opposites of each other by a negative. So you can cancel them out and simply put that there's a negative 1 when you cancel. This is very much like having 5 on the top and negative 5 on the bottom. You wouldn't tell me that's perfectly fine. You'd reduce the 5's and keep the negative, right? It's the same thing. It's just done with a polynomial instead of a single integer. So we do have a negative on top, and now we have an x plus 3 on bottom. Now, notice something that I did, and maybe you did it and maybe you didn't. Did you rewrite limit as x approaches 3? You might have, because I did. You need to. Because when we're working in mathematics, we want each step to equal the next step. And right now, I haven't dealt with the limit part. It's kind of like having a square root that you haven't actually taken the square root of, and you're just simplifying what's underneath the radical. You don't just ignore the square root. You just keep coming along with the square root until you deal with it. The same thing's true for limit here. It's going to say limit as x approaches 3 until we really put the 3 in for x. So we're close to that point now. I'm going to take one more step to rewrite just so you can see cleanly what we have. This step is kind of optional. If you didn't write it, it wouldn't be the end of the world. But this is where we are right now, cleaned up. Have a negative 1 on top, have an x plus 3 on bottom. And can I put the 3 in for x now? I can. It won't give me a 0 in the denominator any longer. So now I actually can. I can put the negative 1 on top. I can put 3 plus 3 then on bottom, and I get a grand total of negative 1/6. How could you confirm that you did this right? What are some methods for finding limits that we just did in section 1.2? Yeah, that's called a table, right? The numerical approach. You could simply put in values that are close to 3 and see what's happening with the original function they gave you, without the reducing and everything. You can make sure that the work you're doing is correct algebraically by verifying that it makes sense from a numerical standpoint. How else could you do it from section 1.2? You could graph it and you could trace, right? Zoom in and trace and zoom in and trace. Now, it's not going to exactly give you 1/6 in either of those views. It's going to give you a decimal approximation. But if you put the decimal or put the fraction 1/6 in your calculator, you're knowing that the decimal approximation is 0.166666, something like that. So as you look at the numerical values it's giving you, or as you trace it along the graph, you're looking at the numerical values it gives there. You should be getting values that are close to that if you've made everything, you've done everything correctly along the way and not made any mistakes. Okay, all good? Okay, let's do one more and we'll pause for today. This problem is more challenging, without a doubt, because what do you see involved? Radicals. There's the division, by all means we see the division, but there's also radicals involved, and we didn't have that on the last problem. So every time you see this, just because you see radicals does not mean you're going to do what I'm about to do. You still have to check, can I put the number in and make it work? So this says x approaches 0. Can I put 0 in and make this work? No, I can't. But if you could, you'd just be done and you do it, okay? So hold off on just trying to make sure you have to do complicated things all the time. Test every single time. If you test this, you will get 0 over 0. Agreed? You will. And you might be looking at this and saying, yeah, but you said when I get 0 over 0, I can factor. I don't see how I can factor that. Okay? And you can't factor this one with the radicals, at least not the way we did in the last problem. So what do? Well, we do something that we encountered, again, in college algebra, or an algebra course maybe in high school or pre-calculus. And we multiply by the conjugate. Now, when we did it before in those classes, the reason we were doing it is we were trying to rationalize the denominator. You're trying to get radicals out of the denominator. There's no radicals in this denominator. The radicals are in the numerator. But we're just going to rationalize the numerator. Okay? So our numerator is the square root of 2 plus x minus the square root of 2. Conjugates are the exact same pieces with the opposite sign in the middle. So I'm going to have the square root of 2 plus x, and I'm going to have the square root of 2, just like the numerator has. But instead of having subtraction between them, I'm going to have addition. But as with anything you do with fractions from pre-algebra, way back when, right? Probably like 5th or 6th grade math is the first time you were working with fractions like this. Anything you do to the top, you have to do to the bottom, right? So I'm going to also multiply by the 2 plus square root of x plus square root of 2 on bottom. So the denominator, we're just not going to do a whole lot with it. We do not want to distribute the x. That's not helpful. So my denominator really is just going to say x, and it's going to say square root of 2 plus x plus the square root of 2. It's just going to stay exactly like that. Very unfriendly looking. We're going to rewrite that limit notation because we have not put 0 in for x yet. We are going to distribute out, FOIL, multiply, whatever word you want to use, the numerator pieces together. But there's a very specific reason that conjugates are so nice. The reason that they're so nice is because when you do the outside terms and you do the inside terms, you get the same thing with opposite signs. So imagine if you were doing this with numbers and you got 5 and negative 5. What happens when you get 5 and negative 5? They add to 0, right? And the same thing happens with these radicals. The inner term and the outer term are the exact same expression except for the sign. One's positive and one's negative. So I don't have any inner and outer terms when I use conjugates. That's the whole point. So what does it mean I have? Well, it means I have the first two terms multiplied, but that's going to be very friendly. What's the square root of 2 plus x times the square root of 2 plus x? 2 plus x. It eliminated the radical, which is kind of the point. I'll put it in parentheses for the moment. And then what happens when I multiply the last terms together? Square root of 2 times square root of 2. Yeah, we get a 2, and then the sign's negative, because one's negative and one's positive. So there's a negative 2 at the end. Now what happens on top? Yeah, this 2 and this minus 2 add to 0. So what am I left with on top?
0.
Not quite. Still have an x, yeah. An x. But do you see a way that that x can reduce? The x in the denominator, right? So this x will reduce with this x. It leaves me with 1 on top. And it leaves me with that square root of 2 plus x plus the square root of 2 on bottom. And my limit notation out in front. Again, the limit notation needs to keep going with you until you put 0 in for x. And this is the point when you can. Now we have the ability to let x be 0. And when we do that, we get 1 over, and it's square root of 2 plus the square root of 2, because the 0 is going to leave me only with the 2. What's square root of 2 plus square root of 2? 2 square roots of 2, right. Web assign very well may let you put that in and leave it. That's okay. When you're doing quizzes and you're doing exams, I'm going to expect that you're going to rationalize denominators, so we're not going to leave the radical in the denominator, at least for those. WebAssign also sometimes is finicky and it won't let you too. It doesn't make up its mind very well, just letting you know. Yeah?
How do you type in powers on WebAssign?
Come see me with your computer, because my version of the side of it looks different than yours, so I don't know from your side. But we can do it together. I know we can. Okay, so even if you just have a couple minutes after class, we can take a look.
I think on like the right side of the screen, there should be a little menu that pops up that lets you do like fractions. And
Like a toolbox?
Kind of like that.
Okay.
Sometimes I see that, sometimes I don't.
It depends on the problem you're working on.
Oh, okay.
Thank you. Thank you guys. All you guys are fabulous. Okay, how am I going to rationalize this is the last thing we're going to do today. we're going to multiply top and bottom by square root of 2. So the square root of 2 is going to stay on the top. And then these two, what's square root of 2 times square root of 2? 2. And then I have another 2 out here in front, making the denominator a 4, right? And I know it looks like you should be able to do something with the 2 and the 4 because they're both even, but one's an inner radical and one's not, so you can't. And when we pick back up on Monday, we're going to hit the trig that I promised you just a little bit earlier, okay?